Welcome back, students. In this video segment, we will cover section 3.3, Trigonometric Identities. I'd like to put this chapter in a framework, in kind of an overall framework of the course, where it sort of plays into our entire course. I'm going to be real blunt about this. This chapter tends to be the most difficult part, or represent the most difficult part of the course. So as we go through these sections in chapter 3, I'm going to recommend that you spend an enormous amount of time on homework, getting used to working with this chapter. Specifically, what makes this chapter so difficult is that we're going to be using the 6 trig functions. Actually, we're using the 6 trig functions all semester, but we're going to be using the 6 trig functions and the algebra that you've learned in intermediate and elementary algebra to combine into a kind of language that's used in STEM field mathematics. Basically, we're going to be combining algebra and trig, and that's been a recipe for difficulty in the course. So rather than making it scarier than it really is, because all you really need to do is practice with it, and you'll be fine. Let's just go ahead and dig in. In this section, we look at trigonometric identities. You're familiar with a handful of the trig identities so far. Examples of trig identities are, say, sine squared theta plus cosine squared theta equals 1. That's a trigonometric identity. You also have tangent of theta equals sine of theta over cosine of theta. These are examples, 2 examples of trig identities. I mentioned in the beginning of the course that at the end of the course, by the end of the course, you'll have probably memorized, I think I estimated between 75 and 85 identities, trig identities, that are going to be important for your later STEM field courses. It's very difficult to find a science where you don't use the trig functions and specifically the trigonometric identities. In this section, we get you used to combining algebra with the trig identities to simplify expressions, algebraic expressions that involve the trig functions. And we do that by something called establishing trigonometric identities. The word establish or establishing could be replaced with prove or proving. So proving trigonometric identities, or establishing or verifying trigonometric identities, is a kind of skill, or develops a kind of skill that's going to be really important for you in STEM field mathematics courses, higher level courses, including calculus and in the sciences, physics, where a lot of the trig functions are used. Okay, so let's continue by establishing, no pun intended, what we mean by a trig identity as opposed to different kinds of equations. So an identity, let's get away from trig just for a minute. An identity versus, let's say, not an identity, not identities. Here, this will be good for us. An identity might be something like, from algebra, 2x plus 4 equals, let's say, 2 times x plus 2. This is considered an identity. What's not an identity might be something like 2x plus 4 equals 7. Okay, so what's the difference between these 2 equations? The non-identity has a single solution. Non-identity, if you subtract 4 from both sides, you get 2x equals 3. If you divide both sides by 2, you get x equals 3 halves. So this thing that's not an identity, this equation that's not an identity, has a solution. Another example of an equation that's not an identity might be, let's say, x minus 3 times x plus 5 equals 0. This is a factored quadratic equation that you had examples of, and this is an example of one that you might have studied in intermediate algebra. This quadratic equation has 2 solutions, okay, versus Let's say on the other side of the line, something that would be an identity that's similar is like x squared plus, let's say 2x minus 15 equals x minus 3 times x plus 5. So on both sides we have the x minus 3 times x plus 5, but on the left-hand side, the equation is not an identity. What separates the equations on the right that one of them had one solution, one had two solutions, from those on the left? Well, look at the first one. The first equation, 2x plus 4 equals 2 times the quantity x plus 2, is true for no matter what x value you substitute in. It doesn't have a single solution. Every number works. Every number is a solution. That's what separates an identity from one is not an identity. An identity has every allowable value of the variable as a solution, as a number that works. On the second equation, x squared plus 2x minus 15 equals x minus 3 times x plus 5. I just factored the left-hand side, and it turns out to equal x minus 3 times x plus 5. So this equation is going to be true no matter what x you substitute in. If you substitute x equals 5 on both sides, or x equals 15 on both sides, or x equals pi on both sides, it will work. So an identity is an equation that's true for every single allowable value of the variable. So back up to my initial reminder of two important identities, sine squared theta plus cosine squared theta equals 1. That's an equation that's true no matter what angle you put in. Sine squared pi over 6 plus cosine squared pi over 6 is 1. Sine squared 15 degrees plus cosine squared 15 degrees equals 1. It's true no matter what you put in. The second equation is also true no matter what you put in for theta, as long as you don't put anything in that makes the tangent undefined or the cosine equal to 0. So these equations are identities. So notice what you're allowed to do when you're solving non-identities, otherwise known as conditional equations. Sometimes I'm not going to write down that word. We don't need it for now. The equation 2x plus 4 equals 7, for example, in that equation, we are allowed to subtract 4 from both sides. That's what I did in the first step. And then we are allowed to divide both sides by 2. I took 2x equals 3 and I divided the left-hand side by 2 and divided the right-hand side by 2. Why are we allowed to do that? Because we are assuming that the equation was true to begin with. We were assuming that 2x plus 4 is equal to 7 is a true equation, is a valid equation. So if you assume that an equation is true, then you're allowed to do things like adding, subtracting, multiplying, and dividing both sides by the same quantity. Now, if you're trying to establish or verify or prove an identity, here's the big difference. You're not allowed to do the same thing to both sides. You're not allowed to do the same thing for both sides. Let me be much more explicit about that with an example. So the example is to, let's say, establish the identity. Establish each identity. Each identity. So let's say A. Establish the identity, say cosine theta times tangent of theta equals sine of theta. Okay, so I'm going to do something wrong in red. It's wrong to do this, to start with cosine theta times tangent theta equals sine of theta, and then to divide both sides, say, by cosine of theta to get tangent of theta equals sine of theta over cosine of theta, which we know to be true. It's wrong to establish an identity by doing this, because in doing that, we're assuming that the equation was true to begin with. When you're trying to prove something, and remember, establishing is another way of proving that something is true, you don't have the luxury of doing the same thing to both sides. So what can you do? the correct thing to do, and I'll put that in green, the correct thing to do is to take the purported identity, the thing that you're supposed to prove, the equation you're supposed to establish, and work on one side independently of the other. Okay? What I recommend is that you draw maybe a dotted line between the two sides. Then pick one side and make it look like the other without working on both sides. So it's correct to work only on one side and to try to make it equal to the other side. Okay. So how do you do that? Well, you get to assume all of the identities that you've learned in the course are true. And this is part of what makes this difficult, is that means you have to remember the identities. Okay. So you are allowed to assume, for example, that the tangent of theta equals sine of theta over cosine of theta. Okay. And then you use some algebra to finish things up. Cosine of theta cancels out. You get sine of theta. It's exactly what's on the right-hand side of this equation, and we never messed with the other side of the equation. We left it completely alone. This is considered establishing. So to establish identities, you pick one side of the identity and try to make it equal to the other side of the identity, independent of working on the other side. You work only on one side. So let's do a few more examples. This is another lecture that doesn't take very long to cover. But unlike the last lecture where we're graphing the tangent and the cotangent and so forth, this section is going to take a lot of your time outside of lecture. I would assume that this section is going to take between, let's say, 3 and 5 hours outside of class, outside of lecture, to look at the homework. Okay, and don't skimp on this section. This is very difficult stuff to learn, and it takes a lot of practice. So the first thing is we pick a side, and there isn't just one way of establishing identities. There's not a side that you need to choose. You don't need to choose the left-hand side or the right-hand side. You choose whatever side you want to start on. Now, as a rule of thumb is one in which that works often, but not 100% of the time. So a rule of thumb here is start on the complicated side and try to make it look like the simpler side. We've been training you in algebra to do basically two things: to solve equations and to simplify expressions. We've given you tough expressions and trained you guys to try to make them simpler. So start with something difficult, make it or long or involved or complicated looking, and try to make it look like the simpler side. Pretty clearly, we should start on the left-hand side then. So the next step is to maybe try to see the differences on the two sides. It's pretty clear. The left-hand side has sines, cotangents, and tangents. The right-hand side just has a secant. So it's not real clear what we should do yet, maybe. So what I'm going to do is I'm going to take the cotangent and make it into cosine over sine, and the tangent into sine over cosine. I can do that because, remember, I'm allowed to assume all the identities that I've learned that they hold true. Okay. Well, it looks like I just made things more complicated. And in a sense, I did. Now I have an expression on the left-hand side that has three sines in it and 2 cosines in it. Okay. So next I notice that on the right-hand side, I have no parentheses, but on the left-hand side, I do. So I'm going to distribute. So here's where algebra comes in. I'm going to distribute. So I'm going to get sine times cosine over sine, and the sine will cancel, leaving me with cosine. Okay, so if I multiply sine times cosine over sine, the sine will cancel, and I'm going to get cosine. Okay, cosine. All right, then I'm going to continue to distribute sine times sine over cosine. I'm going to get sine times sine is sine squared. Sine squared. Okay. Well, Still looks pretty far away from the original, the secant on the right hand side. Well, the next thing I notice is that on the right hand side I don't have any addition. I have one object on the right hand side. I have one thing on the right hand side. Okay, so I'm going to add the fractions cosine over 1 with sine squared theta over cosine of theta. Now what I'm going to do off to the left here is bring up some algebra that's going to allow me to do that. Suppose I have something like a over b plus c over d. Okay. Now in algebra we teach you a quick way of combining these two expressions. In algebra we teach you that you can cross multiply down and get a times d plus that cross multiply up b times c, and then multiply straight across for a common denominator. So this is a formula from algebra, which I'll put in a cloud there. And I'm going to use that formula. I'm going to use that formula right now. I'm going to multiply down in that downward direction. So cosine times cosine is cosine squared. And I'm going to multiply in the upward direction. So 1 times sine squared is sine squared. Oops, I don't want to be red here. So plus sine squared. And then multiply straight across for a common denominator. So all over cosine. And then we stop and try to make it look like the right-hand side. We're trying to get secant out of this. Well, you recognize something? Do you recognize what the numerator is? What's cosine squared plus sine squared of theta? It's 1. Why? That's one of the 3 Pythagorean identities that we teach you. And 1 over cosine is secant. It is over. The left-hand side is the same as the right-hand side, and it has been established. Okay, let's take a look at another example. C. So C, let's say, here's a good one. So cosecant fourth theta minus cosecant squared theta. Somehow, I want to make that exponent a little better. Somehow this is supposed to equal cotangent to the fourth theta. Plus cotangent squared theta. And they look completely different. The sides look, one side has cotangents, one side has cosecants, one has subtraction, one has addition. And the idea that I gave you, the rule of thumb of looking for the more complicated side, sort of falls apart because they look about the same. Well, then we just start on one side. We start on one side. First of all, we notice that if we say start on the left-hand side, we notice that we have the fourth power of cosecant and the fourth power of cotangent on the right. And we have no identities that deal with the fourth power of cosecant. So the next thing we notice is that cosecant squared is the greatest common factor on the left-hand side. So I'm going to factor out a cosecant squared theta on the left. Okay, so there's my algebra. Then I notice I have cosecant squareds on the left and cotangent on the right. So I ask myself, is there an identity that relates cotangent and cosecant? And the answer is yes. We have the identity that says 1 plus cotangent squared theta equals cosecant squared theta. So I'm going to put that in a little cloud over here. I get to use that. So I'm going to use the fact that 1 plus cotangent squared theta equals cosecant squared theta on the left-hand side. Let's make a little more room here. Okay. So cosecant squared theta equals 1 plus cotangent squared theta. Cosecant squared theta minus 1. Well, what am I going to do with that? Well, cosecant, well, Back to the identity. 1 plus cotangent squared is cosecant squared. If I subtract 1 from both sides of that identity, I get cotangent squared equals cosecant squared theta minus 1. Now it looks like I just violated something. In red, I subtracted 1 from both sides, and I just ended up I told you when you're establishing identities, you're not allowed to do that. Well, I'm already assuming that the thing in red is an identity, so I can do anything I want with it. I can add, subtract, multiply, divide both sides by anything I want, except for 0 in the case of division. Okay, so cotangent squared equals cosecant squared minus 1. So this is cotangent. I'm going to replace cosecant squared minus 1 with cotangent squared, and it's almost there. If I redistribute the cotangent squared inside, I'm going to get cotangent squared theta plus cotangent to the 4th theta. And the only difference on the left and the right hand side is the order. And algebra guarantees that I can reverse the order of addition without changing the value of the quantity. That's called the commutative property of addition. I can flip the order of addition. It doesn't matter how I add things, add real numbers. Okay, let's take a look at another one. D. Suppose we have cosecant theta minus cotangent theta equals sine of theta over 1 plus cosine of theta. Okay, now it looks like we're getting really complicated. My goodness, it doesn't look like there's any relationship between the two sides. So you draw a little line between them, and you pick whatever side suits you, whatever side you recognize something, or whatever side your experience dictates that you're going to be most successful with. Now, my experience tells me I should go to the left-hand side. Whenever I'm in doubt with trig functions, I try to convert everything to sines and cosines. It's another rule of thumb that's worked well for me. So I'm going to replace cosecant with 1 over sine and cotangent with cosine over sine. Okay. Well, it looks like looks like I replaced cotangent with cotangent over sine, cosine over sine. Can you recognize anything to do with algebra here? Any algebra to use? The denominators are the same. We already have the same denominator, so rewrite as 1 minus cosine over sine. This is a potentially scary place to be, because the left and right hand sides look very different, very, very different. However, they have the same trig function, sine and cosine, so that's potentially scary. There's a way around this scariness. They look the left hand side and the right hand side now look fairly similar. So the idea now is to force the left hand side to look like the right hand side. Force it to. And by forcing, I mean through algebraic processes. So notice on the right, on my target side, I have 1 plus cosine in the denominator. And I don't have that on the left-hand side. So I'm going to make that left-hand side have 1 plus cosine theta in it. And I can do that simply by multiplying the left-hand side by 1 plus cosine theta over 1 plus cosine of theta. That's just a fancy way of saying multiply by 1. Then see what it gets, see where it gets me. So in the denominator, I'm going to have 1 plus cosine theta times sine of theta. In the numerator, I'm going to have 1 plus cosine of theta times 1 minus cosine of theta. Now it looks like I'm making a mess here. Then take another look at where we are. The mess on the left-hand side has the 1 plus cosine in the denominator, but it has an extra sign. So somehow that sign in the denominator on the left needs to cancel from the numerator. And the only way it's going to cancel is if there's a sine theta in the numerator. Well, let's look at the numerator. Look at the top. 1 plus cosine, 1 times 1 minus cosine gives us the difference of squares. 1 minus cosine squared. What I'm using here from algebra is that a plus b times a minus b is a squared minus b squared. Okay? So I have 1 minus cosine squared over 1 plus cosine times sine. And still, I need to get rid of that sine in the denominator. Look at the numerator. 1 minus cosine squared. I have no identity with 1 minus cosine squared in it. But I do have an identity that has cosine squared in it. I have sine squared theta plus cosine squared theta equals 1. I get to assume that. So I'm going to subtract cosine squared theta from both sides of that. So I'm going to get sine squared theta equals 1 minus cosine squared theta. There it is. I'm going to replace 1 minus cosine squared theta with sine squared theta. Cosine theta times sine theta. And it's almost there. I'm going to cancel one factor of sine in the denominator. I'm going to cancel that one factor of sine with one of the sine factors in the numerator, and that leaves me with sine of theta over 1 plus cosine of theta, and that's exactly what I have on the right-hand side. Okay, I'm going to do one more example, and then I'm going to turn you loose to do the homework on this section. Again, this section is going to take you quite a bit of time to get through in terms of homework. The directions are the same. The directions are the same in all of this homework. Establish the identity, and I want you to take plenty of time to do this. It takes a while to develop the algebraic skills to manipulate the trig functions like this. Okay, so here's our last example. Somehow, that whole left-hand side, cosine theta over 1 plus sine of theta, plus 1 plus sine theta over cosine theta, somehow that has to boil down to 2 secant theta. How is that going to happen? It's pretty clear that we start on the left-hand side. Left-hand side is really complicated looking compared to the right. So the big thing on the left, I notice, is that I'm adding 2 fractional expressions together. And on the right, I only have one expression. I don't have the sum of 2 expressions on the right. So I'm going to use that technique that I described for you from algebra that says if you're adding expressions with different denominators, cross multiply downward, cross multiply upward, plus 1 plus sine theta squared, then all of that divided by, and we multiply straight across. To multiply straight across, we get 1 plus sine times cosine. At this point, there's a common mistake that's made. The common mistake is in expanding 1 plus sine of theta squared in the numerator, you can't distribute the exponent there. We have to remember from algebra that a plus b quantity squared is a squared plus 2ab plus b squared. Fancy way of saying foil out that product in the numerator of 1 plus sine quantity squared. So if I do that, I'm going to get the original cosine squared plus, now the roles of a and b are 1 and sine. So a plus b squared, quantity squared, is a squared, 1, plus 2ab plus 2 times 1 times sine of theta, plus b squared. And then all of that is over the 1 plus sine of theta times cosine of theta. And look at that mess. Look at that really, really horrific looking mess. It's not that bad. What is sine squared theta plus cosine squared theta equal to? It's 1. Plus the 1 that's already there, plus the 2 sine theta that's already there, all over 1 plus sine of theta times cosine of theta. Well, the next step is real easy. 1 plus 1 is 2. Plus 2 sine theta. It's almost there. It's got to be. There's not much left we can do. All of this somehow has got to boil down to 2 secant theta. All of this has to boil down somehow to 2 secant theta. Well, there's our 2. Doesn't seem like there's a secant theta. Well, there's a 2 twice. There's a 2 as a greatest common factor. Factor it out. Can you see what's happening now? Can you see the answer? Can you see that we're going to get 2 secant of theta out of this? 1 plus sine of theta cancels as a factor. We're left with 2 over cosine of theta, and 1 over cosine is secant. So 2 over cosine is 2 secant of theta, and it's over. Okay. So the entire section, once again, section 3.3 on establishing identities, goes exactly like this example. Take one side, try to make it look like the other. You get to assume all of the identities that you've learned for the course are true. Okay, so I'd like you to get started on homework right away. Again, this is going to take you quite a bit of time. Maybe do it in a few settings. I don't think it would be a good idea necessarily to try to do this homework assignment in one sitting. In any case, good luck with your homework. I think that you're going to become really good at this. It's just going to take some time, and I'm looking forward to talking with you again soon.